Good afternoon all. I am going to talk about Pebble guided near optimal treasure hunt in anonymous graphs. This is a joint work with Borun Gorai, Himadri Naik and Supanto Pandit. So as you see in this picture, there is a mobile agent located at some node called S in the graph, and there is some treasure in another node T. The mobile agent has to find the treasure, and there are some help for the mobile agent in form of pebbles. An oracle can put at most one pebble per node on some of the nodes, and the agent has to take hint from these pebbles and has to search the treasure. Now I am going to the formal problem definition and our model. So let G be an anonymous port level graph where delta be the maximum degree. As we know, in case of port level graphs, if degree V is the degree of node B, then the edges going out of V are labeled with port numbers 0 to degree V minus 1 at V's ends, and this is similar to its neighbor's end. So here the degree of S is 5, so we can see that the ports are 0, 1, 2, 3, 4, and its neighbor has a degree 4, so ports are 0, 1, 2, and 3. So S is the agent's initial location, T is the location of the treasure. By P we denote a shortest path from S to T, and by capital T we denote the distance between S and T. We understand that this distance from the initial position of the agent to the treasure is fixed and it is capital D. This agent does not know G, D, delta or T, so it does not have any information. Now an oracle places at most one pebble per node to guide the agent. Our goal is to find a fastest possible algorithm for treasure hunt. Here the oracle, it is understood that it knows all of the input. Now what is our results? We give a treasure hunt algorithm which works in order of d log delta plus log cube delta time using order of d log delta pebbles. Here time is in terms of number of edge traversed by the mobile agent starting from S till it finds the treasure. And the lower bound is omega d log delta time. This is irrespective of the number of pebbles. Now first we will go to our algorithm. Before that we want to give a high level idea for trees. So let's say S is the starting position which is V0, the shortest path is V0, V1, V2, Vd minus 1 up to T which is Vd. Now let's say V0 to V1, the port number is P0. If you take port P0 at V0, you will reach to the next node V1 on the shortest path. Now there are one option that you put only one pebble at V1. The agent will search the pebble. For that it needs to search order of delta many nodes in the worst case, order of delta many nodes, and so it needs to traverse order of delta many edges in worst case to find the pebble. To find the pebble at distance 1. So it will find V1 and then it can ignore the parent port and do the same on V2. So since the distance is D, here complexity is going to be order of D delta. But here we have a better option. What we can do, that this P0 is a number integer between 0 to degree of V minus 1, which is of course less than delta. Now here we require, roughly speaking, log of degree S many nodes to port or to encode the binary encoding or the binary string that represents P0. So here by encoding means if there is a pebble, the agent understands this is 1. In the next node, if there is no pebble, agent understand it is 0. In the next one there is a pebble, agent understand it is 1, and so on. So in this way, by roughly traversing log of degree S many nodes edges, it can find it can get the information about this P0, and then it can go back to S, directly take this port, and it can reach V1. Similarly, it can go to V2 and so on. So we see that this algorithm will take only order of d log delta, as delta is the maximum degree. And here the thing that is helping us is that no two of the nodes like V0, V1, they cannot share neighbor since this is a tree network, and the agent can decode the port sequences which are coded unambiguously. Now, sorry. So, what are the difficulty? So, where is the end of the representation? Because we say that we are using pebble 1, no pebble 0, pebble 1, then the agent can understand, okay, this is 0, this is 0, where does it end? So, we use the simple use trick where using a transform binary encoding, we replace every 1 by 1 1 and every 0 by 1 0. So, the agent reads in a pair, and when it first finds a 0 0, it understands that the string has already ended. So if we want to extend this idea for graphs, the main difficulty is presence of cycles. So V1 can be neighbor of V2, means V1 and V2 can share neighbor. Even V1 and V3 can share neighbor. So if U is a neighbor which is both of V1 and V3, we could have reached V1 to V3 through U, and still it does not affect the shortest path. It would have been another shortest path. But we see that our overcome idea is that we see that any pair of nodes, let's say V1 and V4, which are 3 hop away, there cannot be a common neighbor. Then V1, V2, V3, V4 could not have been the part of a shortest path. So we look at these and we understand, okay, if we can encode port numbers in some nodes who does not share neighbor, then it is possible to encode unambiguously. But there is a problem. Otherwise, we could have just coded in S, then we code 3 of information, we will go to V3. We code next 3 of information, we will go to V6. The problem is that there is no guarantee on the minimum degree of any node. It can be constant. It may not be possible to code all 3 of information in all the nodes. So we need to look for some high degree nodes. And we say that if a suitable node with high enough degree is found around P, then we are going to code multi of information. This is a big thing. We are going to that territory now. So we come to heavy node, light node, and milestone. So what is a heavy node? We say that the degree more than 80 log delta plus 106, we will call that heavy node. All other nodes are light. We will come to this number. Why this number we specifically taking? We will come to this number. And what are milestones? First we assume that some nodes on P are heavy. Then only we will require milestone. Then if that is the case, then some of the heavy nodes in G we use for encoding multiple of information, and those heavy nodes are called milestone. That means we can take milestone which are out of P also, because we are choosing heavy nodes from G. There is one remark why we say that assume some nodes on P are heavy. So if all nodes on P are light, this is very easy case. The simple algo will be keep a pebble on the next node, like one pebble in the next node on the shortest path. And then since the nodes are light, you only need to check order of d log delta many order of log delta many edges to find the next pebble, and this gives us the time complexity of order of d log delta. That's why the assumption on the heavy nodes is necessary. So next, how we will find the first milestone, because when we will get to the milestone, there we can put many information and it is easy for the agent to read all the information and go to the next milestone or towards the treasure. Now here we say that TB, the BFS tree, which is rooted at S, we can compute it in order to the port number, so it is a fixed tree. And Li, the set of nodes at distance I from S on the tree T. So here the nodes which are at a distance 1 from S, they are L1, 2 are L2, and they are well defined. Now we define 4 case based on the position of a heavy node. So case H is that when node S itself is a heavy node, and we call node S is milestone 1 in that case. If S is not heavy and there is a heavy node in L1 which is at distance 1, we say that milestone 1 is the highest degree node in L1. If there is a trie multiple highest degree node, we break it by taking the looking at the minimum port number, which takes the agent from S to such a heavy node. And similarly, we define for case LLH and case LLL. Now milestone 1 is already defined. Now we are defining subsequent milestones, and now all the subsequent milestones are on P. So milestone 1 can be outside of P. We say that it can be on L1 in case of LH. It can be in L2 in case of LLH. So they can be out of the path. But subsequent milestone are on P, and we are defining in this way. So let's say milestone I for I greater than 1 belongs to LJ. Let's say milestone 5 belongs to L20. So that means since it is on the path, it must be V20. Then for milestone 6, we look for the first heavy node on P that is at a distance at least 3 from Vj. So from V20, at least 3 distance there is V23. If V23 is a heavy node, it is going to be the next milestone, milestone 6. If V23 is not, we look for V24. If it is a heavy node, V24 is going to be the milestone 6 and so on. Now what we are doing with milestones, we are encoding in the neighbors of the milestones similar to T network, but in T network we are encoding only one port number. Here we will encode multiple port, a sequence of port numbers due to the high degree of the milestone. It is possible. And we see that any two of milestone are at least 3 of apart. So decoding is going to be unambiguous. Now there is one problem though. The agent don't know delta. So just looking at the degree, let's say the agent is at S, it knows the degree of S since it is at S, but it cannot understand S is heavy or light because it does not know delta. So it cannot compute what is 80 delta plus 106. So this difficulty we resolve by placing some markers. How? We say that the node can identify case H and accordingly understand that S is a milestone 1, S is the milestone 1 if it sees one pebble at S0 and one pebble at S1. That is, if the encoding start with 1 1, it understands that S is the first milestone. If the encoding start with 1 0, no pebble at S1, one pebble at S0, it understands that the first milestone is in L1. That is the neighbor set of direct neighbor set of S. So if it is 0 1, it understands that it is at L2. If it is 0 0, it understands that it is LLL. That means the milestone is at a distance more than or equal to 3. Then we are using another set of markers in S2 and S3. So in case of case H, what is going to be the distance between S and the milestone 2? So it can be 3. In that case, we are putting 1 1 in S2 and S3. If it is 4, we are putting 1 0. If it is 5, we are putting 0 1. And if it is greater is equal to 6, we are putting 0 0. So these are the all possible cases. But when we go to case LH, the cases will change to 4, 5, 6, 7. Why? I will tell quickly. So LH means the milestone can be any node in L1. Now since it is in L1, so the nodes V3 it is in L3. Now V3 can share common neighbor with L1. So V3 cannot be a milestone. So the first milestone can be at V4. So what is the distance between S and V4 then? It is at least 4. So in this case the case is starting from 4 and it is growing. And similarly for LLH these are the cases. Now we show for case H and L is equal to 3 what is happening. So the node agent sees that there is a pebble at S0 and S1. It understands that S is my milestone 1, and S2 and S3 there are again two pebble. It understands that the next milestone is V3. So now what we will do here? So BI are the transform binary encoding of the port P0, P1 and P2. That is the port Pi that takes Vi to Vi plus 1. Here we encode B0. Basically the Oracle places pebble to encode B0. That is to encode P0 in B0, P1 in B1 and P2 in B2. So the agent have the total information of P0, P1, P2. It can directly reach the next milestone V3. In case of L is equal to 4, here you see that no pebble it S3. So looking at that, agent understand this is 1 0 in S2 S3. So the distance is 4. Now accordingly he gets 4 port numbers P0, P1, P2, P3. It can reach to the next milestone. This is the similar case at L is equal to 5. Only the pebble placement changes here and the number of encoding increases. For L greater is equal to 6, there is a slightly different case. So here, see, if L greater is equal to 6 in can be order of D also. So it is not possible to encode all the ports. Then we really need very high degree. So if L greater than equal to 6, what we do? We encode first 3 ports. That is, the agent can go to V3, and then since S is the milestone, S is not sharing any neighbor with V3. So then the next part we can put one pebble at V4, one pebble at V5 till we reach BL minus 3. Let's say the next milestone is V10. So P10, P9 and P8 are already encoded. So the agent can reach up to V3, and if it reach V7, it can reach V10 using BL-3, BL-2 and BL-1. Now how it will reach V3 to V7? Since all the nodes are light, we will put one pebble, basically the oracle will put one pebble at each node V4, V5, V6 and V7. It can go to V7. Now how it will understand that now it has reached to V7 and the milestone is 3 of away? For that, in the neighbor set of V7, we don't keep any pebble. And that is possible since V7 and V10 does not share neighbors. So it finds no pebble in V7 neighborhood except its parent. It understands that okay, I am 3 of away. Now I can use BL-3, BL-2 and BL-1 to reach the milestone 2. So 1 is the next milestone. It is easy. It will find the information in milestone 2 for the milestone 3. So there are more difficulties in case LH though. So the first milestone W belongs to L1 in case of LH. So what is happening? Now, a node is L1 can have common neighbor with S. Accordingly, S0 and or S1 can be common neighbor of that milestone W also, which is in L1. But when we code in the neighbors of W, we cannot use S0 and S1 because they are already used as marker. So then how you can unambiguously decode? So this similar difficulty appears in LLH. We do one simple thing, that let's say gamma be the transport binary string of length z that we want to encode in the neighbors of W. Now we encode 5 copies in N1W, N2W to N5W who are disjoint neighbors of W. So then what happens, that since S0 and S1 are the culprit, they can do the problem. So they can do problem only in 2 of the 5 sets. The other 3 of the 5 sets will be similar. Agent can learn gamma by majority check. So if we look at the figure, you see that this N1W, N2W, each set is differentiated by 2 zeros. And now S1 and S0 can be present in 2 of the places. And then still we can have 3 like here in the figure N3W, N4W and N5W who are same, and agent can understand what is gamma and accordingly it can go to the next milestone. So now we are going to tell that why 80 log delta plus 106 is coming. So this is visible from the case LLH. We said that in LLH, if we go back to the table, that milestone 2 can be at least at V5 because L2 and L4 say are neighbors, so V4 cannot be the milestone. Now that is the least distance. It can also be greater than that, even greater than 8. So in case it is greater than 8, what we are doing, we are again coding first 5 ports so that it goes beyond V4 and last 3 ports. So we are encoding 8 ports in the milestone 1, and then if we compute, we will see that using to do transform binary encoding of 8 ports with separation, we are separating them with 2 zeros in 5 sets. We are doing in 5 sets because S0, S1 can hamper. So this takes 80 log delta plus 106 nodes, and that's why we keep the degree of high degree node more than this. Another thing here I would like to mention, that we consider delta greater is equal to 2 to the power n. If delta less than 2 to the power 10, then we will always see that the degree are less than 80 log delta plus 106 and all the nodes are light and it is a trivial case. Also, we assume that the degree of S is at least 2. So now how pebbles are placed for milestone J, for J greater is equal to 2, we have seen what is happening in milestone 1. So for milestone J, so placement starts from VL0 itself. And then How we say that milestone 3 or milestone 4 or milestone j plus 1 is how many distance apart? For that, earlier we were using S2 and S3. Here we don't do that. Here we just, let's say, gamma beta in binary string that we want to encode, we just prefix it by 111001 or 00. If 11 is the prefix, it can understand the next milestone is 3 of away, and accordingly it can understand the distance of the next milestone. Only when the prefix is 00, again the distance is greater or equal to 6, and we use the previous idea, we encode first 3 ports and last 3 ports, so that and in between we use a single pebble so that the agent can reach to the next milestone. Now, how the agent find the treasure? So searching milestone 1, this is easy. If S is the milestone, it can see that S0 is 1 and S1 is 1. Else it needs to search all possible 1, 2 or 3 length path in case it is LH, LLH or LLL. Now once milestone 1 is reached, the agent decode port number to be followed as paths to the subsequent milestone are encoded, because from milestone 1 we have given enough information, we have kept there so that we can reach to the next milestone. And now how you agent goes to the treasure from the last milestone? So if the treasure is within 3 of, again we keep all the information, and if the treasure is more than 3 of away, the agent goes the first 3 of using the information encoded, and then it follow single pebble at each level, because all the subsequent nodes must be light, otherwise it would not have been the last milestone. So this, in this way, it reaches the treasure. It can understand the treasure only when it reaches that node. And here there are some other difficulties for the case LLL and resolving ideas. I am skipping those for time. So the complexity analysis, we see that moving from one light node to its neighboring light node on P takes at most order of log delta time, and the agent may need to do this for order of d time. So this gives us order of d log delta. Now searching all possible 3 length paths. Consider the case LLL. The milestone is in L3. So the agent starting from S, it has to find all possible 3 length path. And since all S, V1 and V2 are light node, since the milestone is only at L3, so their degrees are also in order of log delta. So finding all possible 3 length path takes order of log cube delta. So this gives us the overall complexity as d log delta plus log cube delta. Now we give a quick idea over the lower bound. So let's say A be an algorithm that takes time 80 on any graph. Now we consider class of all complete delta regular trees of height d. Now let's say the agent is there at some node at some step. Now depending on the pebble present on the node or not, it can take two different two decisions, deterministic decisions, that let's say pebble is there, I will go that way, pebble is not there, I will go in another way. Those two ways can be same, but there can be two options. Now in time 80, agent can follow at most 2 to the power 80 possible sequences of ports. Now since we are considering complete delta regular trees of height d, there are delta into delta minus 1 to the power d many leaves, and when we take the class of all such trees, in each tree we can keep the pebble in different leaves, and the algorithm should be able to find the treasure in different leaves. Sorry, algorithm should be able to find the treasure. Now let's say the time given is d log delta by 2. Now if we find 2 to the 80, considering 80 is d log delta by 2, we will find that it is not possible for the agent to explore all the leaves in this time. So we can say that, safely say that f fails to find treasure in some of the trees, and this gives us the lower bound as d log delta. So finally our results are order of d log delta plus log cube delta algorithm and d log delta lower bound. So there is a gap, but this gap is though very less, it is less than Ellie polynomial in delta, still it will be interesting to close the gap, and then finding or studying the trade-off between number of pebbles and time requirements. Like if we give more number of pebbles than d log delta, let's say we are not giving any number of pebbles, we are giving more than d log delta in order, so is it possible to improve the running time? So this kind of trade-off studying is another direction of future work. So thank you for your patience and hearing.